Okay, let's get started. All right. I will start a Monte problem now. And yeah, okay. So I basically have two files and I'm going to sharing with you. One is the slide. The other one is a full lecture note. Where you can see, whole description of the Monte problem, how I define the random variables, and how do I make use of these random variables to come up with solutions and a statement like this. And state policy can be described in terms of a probability assignment that we have talked about, probability assignment that we have talked about in class. So you can take a look at that. And basically, with the state policy, the probability of winning the Cadillac is 1/3 has been proved. And then you guys can read the full manuscript given here. And then if I talk about switch policy, then the switch policy is defined in terms of probability assignment like this, and probability of awarding a Cadillac is given right here. So you guys can take a look at it. I'll be coming back to this one. So here is the summarized Monte problem. Okay, let's quickly go through it, and you will be on set. All right, so introduction. So Monty Hall is a TV game show. Let's Make a Deal in 1960s. Monty Hall is the show host, and basically there are three doors behind Monty Hall. So behind the one door, there is a Cadillac. And then behind the other two doors, there are goats. Yeah. So three doors, one door, there is a Cadillac. The other two doors, each one has a goat. Okay. And Montiel asked the guest to select one door, and though the guest knows nothing about where the Cadillac is, uh, and guest has to make a random guess. And here is the game, how it progress. So guest to select, for example, door number one without loss of generality. So he could have selected door two, but it's going to be the same story. So here, guess to select door number one. Under this assumption, the Monty Hall opens another door. Let's say, for example, door three, showing there is a goat. So Monty Hall never opens a door where there is a Cadillac. Okay, and Monty then asks, do you want to switch to door two? And that's the trick that Montiel plays to guest. And guest have two options basically. Guest can stay with the first choice, which is door number one, and guest uh, make a switch decision. So switch to the other door. Yeah. And another one is he does know nothing about what's going on. So in such a case, he can make a random guess. All right. And uh, here here this is a famous problem. Basically, stay with the first choice. He get 1/3 of chance to win the Cadillac. And by switching to other door, he get two-third of chance to win the Cadillac. You know why? Because if he stays with the first choice, then it is nothing but a random guess out of three options. And then there is only one success, which is a Cadillac. So one out of three. That's the probability that he wins the Cadillac. But if he made the assumption that uh, my first choice is wrong, and then there are two other options. One of them there is a Cadillac, and the other one door is opened up by Monte. Then he gets the sure chance of winning the Cadillac. So that this depends upon the conditioning that his first choice was wrong. Then that the first choice was wrong is two-thirds of a chance. So once once the guest make the conditioning that his first choice was wrong, then it becomes a sure event because Montiel always opens up, a door behind which door that there is a god. So the other door that the guest has to select, it is going to be surely the Cadillac. Okay, so that's the case. That's why by switching to other door, the guest has a winning probability which is two-thirds. Okay, and random guess is basically half and half of these two policies. All right, so that's the game process, and but this answer for this famous problem is well known. There are many different solution approaches, but in this class I am trying to utilize this famous example uh, as an exercise for you to practice the primer on probability and random variable note that I gave you. There are, total probability theorem, conditional probability, joint probability, and three axioms of probabilities. I want you to make use of only these rules that I have on the primer on probability and random variables, and then come up with uh, explanation of this answer, which is one-third for stay, two-thirds for switch. Okay, that's the motivation. So here, I have a formalization. Basically, I will define four. I will define four random variables. First one is award variable, which is when A is equal to 1, the award is Cadillac. When A is equal to 0, the goat is the award. So this is over the random variable, and we will determine probability that A is equal to 1. And then once you have determined that, then probability of A equals 0 is found, right? That is just nothing but 1 minus probability A is equal to 1, right? So because this is binary random variable, so this random variable will be fully defined once we have the answer for each policy, stay policy and switch policy. And then SI is the door selection uh, at step I. So there are two steps. First, door selection made by guest, and the second door selection made by guest. Okay. The first door selection and the second door selection on the stay policy should be the same, right? If, for example, if guest made a door selection number one, then the second door selection on the state policy should be S2 is equal to 1 as well. Okay, so that's it. And then the Montreal Show crew members place the Cadillac behind one door out of the three, right? And then it could be door number one, two, or three, and then it is going to be random, uniform random variable. So P equal to one with the probability one third. P is equal to 2 with a probability of one third as well. And then P is equal to 3 with a probability of one third. Yeah. So those are the probability assignments. So SI and P, they are uniform random variables out of three choices. Okay. Each one is a uniform random variable out of three choices. Okay, and Monteor is the show host. Opens up a door, and then he always opens up a door where there is a goat behind it. Okay, so and then this uh, random variable will be fully defined when we have the probability assignment. Okay. All right. So goal is compare the two policies, stay versus switch. Okay. All right. So let's jump to the conclusion. Basically, when you read the lecture note that I have just shown you, then you will have a full statements. Basically, lemma says without loss of generality, we may assume first choice is the one, right? The guest makes his first choice, and then without loss of generality, we may assume that door is door number one. It could be door number two, door number three, but without loss of generality, this selection doesn't matter. Okay, as far as concerning probability of A is equal to one. Okay, so probability that award is equal to one is exactly the same as probability that A is equal to 1 given S1 is 1. Okay? And then that is one third. This is what we are going to prove. Okay? That means award random variable and S1, they are mutually independent. Okay? All right. And then this under stay policy, we found that the probability of stay, which is this one, is exactly equal to one third. We will prove that using the only tools that we learned in the primer note. Okay. All right. Probably total probability theorem, conditional probability, joint probability, and that's it. We are going to only use those theorems, no other theorems. Okay. All right. And uh, so basically on the stay policy, like I said before, winning depends only on the first guess. Okay, because the guest has to stay with the first choice. And the switch policy, like I told you, probability of winning the Cadillac is two-thirds because he is betting on the condition that the first choice was wrong. Okay, and then that probability is two-thirds. And then the conditional probability becomes a probability of a sure event because Montiel always open the door where there is a goat behind, and then rest of the door, which is one door that must have a Cadillac behind it. Okay, so that is the reason that this is two-thirds, the probability of winning Cadillac on the switch policy. All right, but this one is well known, but we need to prove by making use of the tools that we have seen in the probability note. Okay. So there's another explanation. So switch means change to the other unopened door. Okay. And that is going to be two-thirds. Reason. First choice correct with a probability of one-third. First choice is wrong with a probability of two-thirds. So if wrong, if we made that assumption, switch guarantees Cadillac. Okay, so that's uh, the statement we are going to prove in the lecture note. And then comparison. So state policy, winning Cadillac is one-third. Switch policy, two-thirds. Okay. And then the conclusion is basically switching is much always better. And then once we have fully described and fully prove each policy with the probabilistic tools that we learned in the primer on probability and random variables, then we can go deeper into problems. For example, we may extend the problem to non-uniform placement. You know, for example, the crew members prefer to put Cadillac behind the first door with a probability P. And then the second door, third door, same. Okay. This could be possible, uh, but this type of problem can also be dealt with the tools that we learned in class. Okay. And then imperfect information. Another extension could be the crew gives secret information about the Cadillac's location, and then this information is known to be wrong with the probability of data, where data is a number on this interval from 0 to 0.5. Then smart guest computes posterior probabilities, knowing this. And then he need to again have to analyze the two different policies, stay versus switch. So these are the two extensions. All right. So basically, that's it for today's class. And uh, I want you to take a look at this full note in order to understand how we come up with the probabilities. Here I define uh, the, uh, the random variable A, and the A is equal to 1 for Cadillac, 0 for goat. All right. And then there are door set, which is 1, 2, 3. And then the first door selection made by the guest is S1. And that's the first door selection. And then second door selection is when I is set equal to 2. And it denotes the second door selection. And then the distribution is distribution for S1 is uniform. All right. And placement random variable P uh, has an element 1, 2, 3, and this is also uniform random variables. Okay, and behind denote the door number, the Cadillac has been placed. Okay, all right, and then Monte Hall random variable, and then once we figure out the problem in this node, we will be fully aware, what type of random variable Monte Hall is. Okay, and then so distribution for S and P are already given, and then we will talk about distribution for A and Monte Hall as we explore the problem. Okay, and then the lesson that I would like to give you is that you will be able to go deeper into variety of other problems once you are able to use the knowledge of given in this note. Okay, so I want you to take a look uh, because it is tedious for me to go through the whole whole note line by line. So I'll just briefly give you an overview. Okay, so first one is showing that the random variable A and S1 are mutually independent, which is to show that this probability right here is true. Okay, the conditioning doesn't matter. Okay, and then the proof is nothing but starting with the probability that A is equal to 1, and then use what? Total probability theorem, then probability A is equal to 1, S1 is equal to 1, plus probability A is equal to 1, S1 is equal to 2. And then S1 is equal to 3 right here. So this is total probability theorem. And then using the conditional probability, definition of, and then we can transform each one of these joint probability into this. Okay, and we note that this prior probability, which is probability S, 1 is equal to 1. So this should be S1. Sorry, this is a typo. S1 is equal to 1. Yeah. Yeah, and I think this should be I. Sorry about that. So and then here this is 1. I will fix this note and then update it after the recording of this video. All right, and then given that, then it becomes this. All right. So once we have proven that probability A is equal to 1 is equal to probability A is equal to 1 given S1 is equal to 1, then we can say that these two random variables are mutually independent. All right, so the note is like this. So I hope that you can take a look at the whole note and then understand how we can describe and analyze the two policies and then find out the exact probabilities. So for uh, the state policy, now we want to prove this part. Now, prove this part. So stay with this. Start with this, for example. Probability is A is equal to 1, given S1 is equal to 1. First door selection by the guest is door number 1. All right. And then use the total probability theorem again for P. So here, P is equal to 1, P is equal to 2 right here, P is equal to 3. So we have to add all of them because this is total probability theorem. And then once you have written down this line, you can immediately see that under state policy, right? Here, state policy, uh, first selection of the door is 1. Then on the state policy, the guest cannot change the door, right? Then the placement has to be at door number 1. Then this will be the probability that you will hit Cadillac. What about this one? This one, the crew has placed Cadillac behind the door number 2, but the customer, I mean the guest has to stay with his first selection. So the chance that A is equal to 1 is equal to 0. And then same story with this one. First selection is 1. Crew placed the Cadillac behind door number 3. So the probability that A is equal to 1 cannot but be 0. So these two items, the probability is 0. The first item is 1/3. Okay. The full proof is given right here. Like I said, this is too tedious for me to go through all of them. I want you to take a look at them. And then if you have any question, you can ask me. Okay. And here is the, once you have gone through this note, then you will understand the state policy can be uh, decomposed into probability assignment. Policy can be probability assignment. Policy can be implemented in terms of probability assignment. So basically, uh, that's what you will see when you study this part. All right. Now I'm going to jump to conclusion that once we have understood this part, you will be able to prove this uh, line. Okay. Under state policy, the probability is 1/3. And on the switch policy, now you can define the switch policy first, using the probability assignment. Okay, right. So that's the probability assignment is given right here. And then without even without this, you could be able to calculate the switch probability of switch policy, which is this line here again. Probability that A is equal to 1 is equal to probability A is equal to 1 given S1 is equal to 1. And then we can decompose this into P1, P2, P3 again. Now, under the switch policy, if you condition on S1 is equal to 1, S2 has to be some other door, some door other than door number 1. And then the placement of the Cadillac is door number 1. So this probability cannot but be 0. And then the probability that placement is behind the Cadillac placement is behind the door number 2, and then the guest made the first selection, which is door number 1. Then Monte Hall opens up in this case because there is a Cadillac behind the door number 2. Monte Hall opens up door number 3. Then the guest cannot but make the last door, which is door number 2. So the probability that A is equal to 1, this joint probability cannot but be 1. Okay. And the probability of placing the Cadillac behind door number 2 is 1/3. That's why we have this. All right. So this is 1/3, and then Montiel opens up in this case. Door number 1 was selected by guest, and then Montiel opens up in this case door number 2 because there is a Cadillac behind the door number 3. Then guest make the second selection, which is 3. All right. Then it becomes a sure event that the award is Cadillac. All right. In this case, the probability is 1/3. 1/3. So adding the 2 is the probability is 2/3. And then there is a full proof of that line. And then because this is again tedious, I will not go through here, but you will be able to understand line by line. And then I have this comment line by line explaining why it is so each line. Okay. And then there is a conclusion and then summary of the two theorems. And then here are the extension problems, non-uniform placement distribution like this. And then if you just understood the Montiel problem using verbal description, you will not be able to attack this type of problem. But since we have gone through this probabilistic analysis, then you will be able to go through thoroughly, and you will be able to solve this type of problems as well. And then another one is imperfect information that I talked about in the summary slide. All right. So that's going to be the end of today's lecture. I want you to take a look at this lecture note and uh, apply the rules that we learned in class. All right. That's it for today. If you have any question, use the Kakao Talk room and then let me know. All right. That's it for today. Thank you very much.